Log on, tune in, find out. Another good idea from Cambridge.
You hear me? Okay, good. So for this talk, what I wanted to do is present some practical problems for which solution we needed to deploy some sort of mathematics. But still, I didn't want it to be about classical cryptography, but preserve some substance of theory to show how a little bit of theory can solve your problems your practical problems. So I'll try to walk through a number of ideas, a number of situations, some of which I think are rather entertaining during those 45 minutes. And the list of the nice things that I collected throughout the year were about those topics: how to look cryptographically better, how to generate 3D wire meshes, how to scatter a secret physically, how to identify quickly, and also multiple signatures. So because I wish to overview these and I don't have a lot of time, I'm not going to present excessive details, but rather the ideas and the results, what we proved, what we constructed, show you images. And in case you want to know more, just send me an email and or come and discuss them. So let's start with the first one: how to look cryptographically better. So I was required by one of my clients to fill such a stupid diagram in a tender. So I couldn't do otherwise than fill it intelligently, because I have 2 PhDs that this client is actually sponsoring. So as you can see here, you have on this diagram a signature, encryption, antivirus, and then the quality of the organization, whatever that means, plus the experience of the management. So this gives them a way to assess the strengths of an offer, and I was trying to collect the information to try to help them to do this diagram. It was in a tender for PKI and security services, and then a natural question came to my mind. So can I find an ordering of the axis that minimizes the visible surface of the competitor but maximizes the surface of my client's offer? There is nothing dishonest about it. If the quality of the organization is still 1, then it will still be 1. The only thing is that I might put the organization, let's say, between the signature and the encryption, move the antivirus near the experience, but what I want is to look better. I have a big surface and a small surface for. So it's a nice application of the theme of this workshop, I find, because it's to optimize a subjective practical security problem by non-subjective methods, and it shows how actually practice and business sometimes drive us to find non-evident ways to arrive to a null result. But here is the solution. So a little bit of mathematics and a proof by induction will allow you to find this. So if you assume that the characteristics of your offer are ordered x1, which is the biggest one, x2 is the second biggest, and so on. So in this case, x1 would be antivirus, and x2 would be the signature, and x3 would be encryption or experience, because they seem to have the same weight. Then to maximize your offer, here's how you have to order them. You put the biggest here, and then the second biggest, let's say, to the right, and then this one here, and then this one there, this one here, this one there, and this is going to maximize the visible area of your diagram. This is easy to prove. If you want to minimize someone, to make him look smaller, what you have to do is put his best here, x1, and then put the least one here, and then the second biggest one here, and alternate the other way around. So actually we used it, and we won the I don't know if this because that we won the tender, but it was very well accepted. Hence we can develop a general theory of that. So buyers are not always stupid, so they may quickly see that the ordering of your xi is not identical between the offers. In my case, I purposely left them non-identical to make our one look huge and their one look small.
star shape, which might look quite positive as a message.
It depends. It really depends. And yeah, but, you know, you can. It's an interesting. So the problem that I tried to tackle afterwards was to find an ordering of the axis which is identical between the two competing entities, but in my favor, meaning that the ratio is the best for me. So I cannot just order, because they would say it's unfair if we don't use the same axis. So given his xi's and given my yi's, how can I find an ordering of the property so that the ordering is the same, but the ratio plays in my favor? And what is more complex is how to look good when you have several competitors, let's say 2 or 3 of them, and find the metric and then optimize this. So there is quite a lot of room to do research here if you want, and further get results. So the second practical problem that I wanted to show you is the construction of 3D mazes. Also came up while working in security. So what is happening now is that the industry is moving towards 3D chips. It's called the system on chip, SoC, and many metal layers are being stacked on chips. And once you have stacked many metal layers, let's say 10, 12, then you can flip one on the top of the other and then double it. And the question that I try to tackle with one of my PhD students is, can we use this for increasing the security of the chip, those many metal layers? So we started with the Hamiltonian circuit. You all know what it is. I collect all the points in a graph using a path. And then what you can do is that if you break simply one of the connections, you can use it to inject a signal and collect it later. And this already exists. So in the 2D world, we have wire meshes such as this one that run on the surface of a chip, and the chip is injecting into them data and tries to see if the data is being caught out properly. And in some cases, there is even an analysis of the response of the analog response of the maze. So our idea was to do this in 3D, to generate those structures, and to put inside the cage a device or some sensitive circuit, and have so you can see that there are planes here. This is the metal layers. And the idea was to put something in the middle and have it inject signals and collect them back. So the question is, how do you generate? We didn't want it to be regular. We wanted to be a Hamiltonian circuit that would collect many points, but we still didn't want it to be regular. So so the idea is that this would have been a little bit too simple. So we found an algorithm that I'll show you that allows you to generate a circuit like this. So what the algorithm generates for us are the floors that then we can give to the silicon designers, and I'll show you photos of the circuits that we construct. But it was way too simple, because the problem here is that if you put this circuit and you look into it from the side, you can actually see very regular holes. So I'll show you this. So let me show you here. So if I take this circuit and I rotate it, you can see those holes here that come at regular spacings, and you can try to go and drill through them. So what I wanted to do is put a cage inside a cage, which actually gives something like this. This is what we built from copper supplies before we went to circuit production. So here we can see one Hamiltonian circuit that was generated with the algorithm, and then this sort of Hamiltonian circuit was embedded in a bigger one, passing through the holes inside. So these are the sort of structures that you get. So how do we generate them? So we have several, it's very interesting because we have several ways to do so. You can depart from a regular one, which is easy to construct, and then rewrite it using rewriting rules that can allow you to break edges and connect them in a random way. So you run this on your cage until the cage becomes random enough to your taste. Here you can see what is happening as you randomize it. Basically, you depart here, we depart with something which is very regular, with, as you can see, these long edges, and then slowly you transform it, and then you transform it again and again. And another algorithm that we use that I can describe here in 2D is you take the plan and you form small squares of 1 by 1 by 1, and then you can rewrite the squares either using this rule or this rule randomly. So you flip a coin, and then you rewrite your squares. Now once you finish doing this, what we do is we fold it in 3D. So I take what happened, what's generated here, and folding it like this, like a millefeuille, you know. And then you apply the rewriting rule. So what is the rewriting rule? For instance, if you find a U connected to somewhere, and the U can be either resting on 2 pillars, or depending on 2 pillars, or having 1 pillar below, 1 pillar up, you don't care. And this U is followed in front of it by a bar, which again has either 2 pillars up, 2 pillars down, on 1 up and 1 down. Then you can transform it, you flip a coin and you can transform it into this one. And you can see that it doesn't break your Hamiltonicity, because you were collecting those points, you're still collecting the same points. And then you run it over and over and over again on the structure, and you apply your rewriting rule. And what will happen is that eventually you are going to you see that here, for instance, points disappeared and so on, so they get connected in the middle. We stopped here the algorithm quite early so you can see the effect, because after this it's difficult to visit. So now you can generalize this to 3D. So in 3D, what we do is that we depart from the 6 basic 3D Hamiltonian circuits, do exactly the same as we do for 2D. So you place them, and then you connect them using rewriting rules. And this gets randomized much quicker. So here I can see before we do the rewriting, so you can see that you have individual structures here, and they're not connected to anything. So each of them is independent, and those ones are just sitting there. They have the same role, exactly the same role as those squares that you can see up there. And then once you did this, you start rewriting them, and it glues your structure, and then you can try to go for production and do all sorts of smart things with it. So on silicon, so we went to produce those wire meshes. So the idea here is that the wire mesh is not going to be only around the circuit, but it is going to be penetrating the circuit, meaning that we are going to have lines that go across the circuit and coming out of the outside of the circuit. So you give your constraint, and the algorithm runs to try to cover the circuit with as much mesh as it can. And basically, once you go on silicon, this is what you look. This is the top view of the cage. The device is running in the middle. And now what we're trying to do is to go for a dynamic solution. So the dynamic solution is basically having in given parts of this 3D structure an active circuit. So this active circuit has a very small hash function inside, or sort of Mach hash function, whatever you want, how to call it. And then the device which is protected inside is injecting a message that it shows randomly into the wire mesh. It goes to the first station, gets processed, which transmits it to the second station, gets processed, to the third, to the fourth, to the fifth, and then comes back to the circuit who sent it, who is going to check that it was not modified. So if you're trying to hit this structure, either by disabling one of those processing stations that has an internal state, a volatile internal state. They cannot record information, but they remember what they were processing. Then what would happen is that the circuit could see that you are breaking something around it. So it's not very original in the sense that in the software industry they have what they call the canary, which is something sitting on the stack, and if you come and do a stack overflow, you see that the something happened. But here it's sort of physical canary, and now we're going for doing this. So here we have plenty of theory and nice things to do, which are practical as well, and it also has applications and funding for PhD students. So it's good. So this is something that we are processing. So if you're interested in this, you can email to me.
The real circuit that has to do something, you have to get your data in and out also.
Yes.
Do you provide paths through your
Yeah. There are passes for the power supply and for communication with the circuit. So the idea is to put inside only very sensitive circuit parts, and to be able to communicate with it, provide it power, and provide input and output inside. So there is a dedicated line that allows to do so. Now, another interesting question that we have on this one is that assume that you have many stations. Let's say, assume that tomorrow I'm going to have, I don't know, let's say 50 metal layers that I can really do many stations that are really interesting and that have some processing capacity. So for the time being, now we go for 12 stations. But if we are having more, it might be very good that if I'm the protected circuit, I don't need to rehash what everybody was doing, but I have a shortcut that allows me to compute very quickly all the cumulated effect of them. So we know functions like this, like for instance exponentiation. We could compute g to the power of x of y of z and whatever, and I have only to compute x times y times z and so on, modulo p minus 1 if it's a small number. But still this is costly, meaning that we don't like that much to do an exponentiation in a small canary which is doing only that. So we're trying to think about combinations of functions that would at least to do us some shortcut. The other problem that we meet when we want to implement this is the internal state, because it's not only that you have to compute a function, but we still want it to depend on an internal state, meaning that upon reset those things are zeroed, and then they start to accumulate information, because I want to know that they are still connected and nobody is fooling me with as the process goes. And having a function that allows both to have a shortcut and both to have a state is not evident, even if you work with those exponentiation. Well, we did find one. It's based on pairing, so we're not going to put pairing in the canaries, but yeah.
You mentioned that you wanted this property that is hard for somebody to drill into your
This
box.
is why we use two cages.
Yeah. Can you formalize in some mathematical way what this means? Is it like you can't see deeper than a certain distance into the box?
Yeah. Mathematically, what would happen is that basically, if you look at an edge, you're going to have the metal layer here. Okay, and I want this distance to be exactly the same as this distance, so that when you have, if you look into the way in which a cube looks, if you have because you have a Hamiltonian path, what you would see inevitably is this. If you take a cube and you look at it from the side, you're inevitably going to see this, because it's going through all the, so copper is here, copper is here. Sorry, I did them in double.
We can take it offline if you like.
Yeah. No, I just did them in double. So yeah, here is the second one, and here is the third one. So basically what would happen would be that all distances here would be equal. Like this distance is equal to this one, equal to this one, to this one, to this one, to this one. This is what you would see if you look at it from the side. If you look at this structure from the side, what you would see is this. So you draw actually a line, and then you can see that you have holes inside. Now, if this hole is exactly the same size of this, meaning that this space that you can see here is the same as this one, it means that the inner cube is going to block the visibility of the space. So of course you cannot do it exactly the same, because if not you have short circuits, because they would touch each other. But I would like to have a very thin space between this round here and those edges here. In such a case, when you look into the device, you cannot access it through those, because you have two circuits that are embedded in each other. Now you can, of course, so there are interesting things. For instance, you cannot find a 3D Hamiltonian path like this for odd cubes. Because simply you need to have as many ways ahead as you have many ways backwards. So if you're working with an odd cube, you have to remove a point, for instance, the middle point. So when you are talking about the embedding of cubes like this, the odd one, which is inside, doesn't have its central point.
Can I add something?
Yeah.
Why do you need it to be Hamiltonian? I mean, there could be 2 cycles or a few cycles.
Yeah, because I wanted to try to cover as much as I can. I wanted to cover as much as I can my circuit, and when I'm going to do it in a dynamic way, I want any break to be detected.
Yeah, no, I understand that, but I'm just saying that, like, if these restrictions are artifacts from, we are going to have a single Hamiltonian circuit.
Oh no, you can have 2 of them if you want.
Yeah.
But it will do a double work of injecting signal and so on. Of course, there are many variations here. We're talking about products, so you can just imagine all sorts of. You can have several ones. So it was quite interesting theory to develop, and there are many open questions and algorithms that you want to make efficient and so on. So another question related to I don't know how much time I have. Another question related to physical security and indirectly to crypto is how to scatter a secret. So when you're manufacturing chips, especially complex chips, and you want to debug them later, you can go and try to probe signals in the chip using this kind of devices. It's called a probe station or probing station. So here you can see here the needles that go on the chip, and you can even probe several of them. Like here you have a board that can allow you to probe 12 points on the same circuit. So you can go and try to reveal what is happening on a given wire. And now there are even electromagnetic probes that are extremely small and that allow, with a lot of precision, without touching even the circuit, to reveal what's inside. Been developed by the team of Lionel Torres at Lyon. So with one of my students, we wanted to find protections against those devices. And the protections that we wanted to find were first classically oriented to do secret sharing as we know it, but very simple secret sharing. So the simple secret sharing means that we're going to take a bit and we're going to share this bit as the XOR of other bits. So I have a secret bit S. This is my information that I want to keep somewhere in my circuit. And how do I record it in memory? I simply compute SIs that XOR into the information that I want, and I scatter them over my circuit. And what I want is that I want each share to be as distant as possible from each other to make the probers attack hard. Why? Because what we noted is that actually if the bits are near each other, it is very easy to make a small deviation of the electromagnetic probe and probe the bit which is nearby. But if you have to lift the electromagnetic probe and reposition it again, then you have to do a lot of work and you lose in precision. So what we wanted to do is find a scheme where we take a piece of data and we scatter it physically on the chip in such a way that makes the prober's task as difficult as possible, meaning maximizing the distance between the bits. So you can intuitively illustrate this problem as you have a chessboard of n over n of n over n, and you have n sets of n pawns, and you paint each set of pawns in a specific color. And what the defender needs to do is to place the pawns on the chessboard in a way that maximizes the minimal distance between two squares occupied by identical color pawns. So how do you do this? You can, for instance, use this tiling formula. So I assume that my chessboard is a product of A by B, with B bigger than A. And fxy is the function that associates to the geographical position xy a color fxy. And how do you calculate the color? So what you can do is, for instance, this. So you begin by basically computing x over a, the coordinate x over a modulo 2 to see the parity of x over a, and you're going to use this here. By multiplying by b over 2, you add to it y, the other coordinate, and then you reconstruct this. So the result that you get is a periodical function, and the minimal distance between 2 points that are the two different points that have the same color, you can see that it's either a shift of y by b or by a, with followed by a shift of b over 2. So the distance that you're going to get is the minimum between b and this. So you can try to optimize it by making those two quantities equal, which gives you actually a ratio a over b, which is the root of 3 over 2, meaning that if I'm placing I'm choosing an a and a b such that the ratio between a and b is roughly this, then I get an optimal distance. So here you can see how it looks. So here we run the algorithm for n equal 12. So we are spreading 12 bits. Of course, it is very regular, and we'll see about regularity later. So this procedure will provide this. So what if you cannot select A and B freely, which is generally the case? So we have less intuitive algorithm that you can see here. Had to do quite a lot of math to make it run, but it still gives you a very nice result. So this is, for instance, for n equal 11, the result of the placement of this algorithm. So how good are those algorithms? So there again you have quite a lot of math, so you can surprisingly on those algorithms quite easily prove upper bounds and lower bounds, the best distance that you can ever get, and for this specific algorithm a bound on the distance, so lower and upper bound. And this made us look into an entire area that is called tiling. So people are studying this, how you can design, how you can cover with a given number of colors surfaces of different types. And you can see that what we did is extremely close to this. So what we are looking into now, and what is very interesting for the people who are doing chips, is to try to find aperiodic solutions that are very, very interesting from a security standpoint, where I cannot foresee what is the point that corresponds to another share of the same bit. So today we just approximate aperiodicity by generating a periodic solution, such as the ones that I showed you, and then just swapping randomly some adjacent memory cells to introduce aperiodicity inside. But this comes at the cost of degrading the distance, because the minimal distance becomes smaller. So finding solutions that are aperiodical and do not degrade that much the distance are desirable. So the ideal object that we are trying to look for is this one. It's a function that we call fk of x and y that gives an aperiodic solution to the scattering problem with a good d, which this is basically the theoretical, the best thing that you can find. This actually plus O of 1. So so this is what we're trying to look at, and you wouldn't be without noting that we put a small k here. So what is the role of this k? The role of this k is that we want to have a parameter k, which is a key, with the property that even if you learn the value of fk xy for L positions, meaning that you have an oracle that tells you this is bit, that this is the share of this bit, this is the share of this bit, this share of this bit, guessing the color of a next share is going to be difficult. Basically, we ask that your knowledge about it would be essentially guessing. So we don't have this construction as yet, but it is something interesting because it's not really block ciphers, it's not max, but maybe there are intelligent things that we can imagine about this.
Do you mean 1 by k?
You have n square points.
Yeah, but I don't see how anything depends on k.
K is a key. K is a key,
Okay.
meaning that your scattering scheme has a key. It's a keyed scattering scheme. So you choose your k, and then it gives you a coloring. Okay. Yeah.
The capital L, do you really want it to be just smaller than n squared, or is it somewhere smaller than n squared?
N squared is the maximal number of points that you have in.
Exactly, so if you just have it equals n squared minus 1, then that can't work.
Of course.
What's the rough size of L you imagine?
Usually, what you would do is that you would say, I can guess by some measurements a few, let's say 3 or 4 or 5 positions, and I have, let's say, 1,000 of them. So what does it allow me to learn about the scattering that the person was using? So
your method seems to strictly depend on the fact that all the bits on the memory are in fact key bits that you need to scatter. So I could assume that there's a lot of other bits around that don't need to be scattered. Then you get a very different optimal solution.
yeah, you might.
So how realistic? I mean, I don't know, right?
The origin of this problem is actually a company doing silicon that was kind enough to take a few PhDs, and they said, okay, we want you to find some differentiating crazy ideas to help us, okay? So we like when they ask questions like this. So all we had to do is just brainstorm for a couple of days with the PhDs, and then we came up with many things. And we had let's try and give it a try. So we didn't really look into a formal, model of the thing that says we need to do this and that. But we asked them, what can you do? What are the tools that you have? What are the threats that you want to protect yourself against? And we came up with those things. So probably if you say that there are holes inside, it can even maybe be, you can also say that you can scatter with it some random data that doesn't depend on anything, or shares that do not depend on anything. But there is room to clarify to. Okay, so we move to another one, which is 2 minutes.
It's 2 or 3, yeah.
Okay, so then we'll probably better move to questions then. Okay. If you want to see how to identify quickly, and if you want to see how to do multi-signatures, which nothing to do with crypto.
How quickly, in less than 2 minutes.
You said it's going to be quick, so yeah.
Yeah. It's okay. Okay, I'll try to run through it. So 2 minutes. Okay, 2 minutes. But I will not have the time to do the last one. So how to identify quickly? So this is again a company which is called Sagem, who took a PhD student for doing biometrics, actually called Morpho. And they asked us, they said, okay, we have this issue of having huge databases, and we want to identify a person in the database. So they said, can you do something about? So they had algorithms for identifying, and they would and they said, what can you do to optimize them? Can you think about something? So basically, how the biometric identification worked in their case, it's very simple. They have a collection of template B1 to BK, and they have to compare them to an acquisition B. So basically, B1, BK are the employees, and B is the guy who is standing at the gates. And the goal is to determine which of the BIs is the closest to B, and hence identify the guy. So you assume that they have an oracle, a magic box, and this magic box you put inside B and BI. So you extract the template I from the database plus the one who is standing on the gate. It tells you yes or no. So things in reality are not like this, because you see that I chose a specific box, and this box has a hole in it because you have to pay money each time that the box is telling you yes or no, because this costs you time. So this was the problem actually. So they said, can you optimize the box? And you look into the algorithm in the box and say that maybe we can optimize it, code it in a further way. But I didn't want to enter into the box, because when you look inside, it's all sorts of B-splines and things in mathematics that I don't like. So I wanted to try to shortcut this. And you know that when you paid the K euros, then you identified or excluded the guy for sure. And I said, is there a better strategy? So it turns out that yes, if you add some extra assumption, but so I will add the assumption, then I will remove the assumption. So the first idea is that you record for each user not only the template B1 to BK, but also, let's say, the height of the person. So it's an extra assumption. Then we'll remove it, don't worry. So when a person comes to register, I take his fingerprint and I measure his height. Now, obviously, when someone arrives to the gate, I also measure his height. So I have H and B, and I have to match it against HI and BI. So what can I do? I can try to match it in an order where I sort H minus HR in an increasing order, and I start with the ones who has the best height, meaning that are closest, because the probability that it is this guy is higher. So if I found him, it's game over. If I didn't, I pass to the next. Okay, but there can be a noise. Okay, but this is cheating, because I need to acquire an HI, meaning something more than my template B. But what we can note is that actually what I called height here, just for us to understand, is something that I can extract from the template itself, from the fingerprint. For instance, what I call the height can be the number of minutiae per square centimeter. So I measure something on the template, I record it near the template, and then I use this to do a pre-screening, a very quick pre-screening. And then what you can do is compute those for first time, and when you install a template, and then when someone comes to the gate, you pre-recorded all those data near each template. You simply compute those, and you begin to do your comparison. So okay, so this is very good. And the problem, how about having two scalars? Now let's assume that I not only have the height of the person, but I also have the IQ of the person. So this is a very strange identification scheme where someone comes to the door, I say, I measure your height, give me your finger, please fill this IQ test. Okay, and then I compare. And then I say, okay, it's him, it's not him. Now he filled the IQ test, then I can, but how do I compare? How do I compare? Because how many IQ points are worth 1 centimeter in height? Okay, so it's very difficult to compare. So okay, there is a no-brainer is that you check first those ones that has the IQ which is closest, the differential in IQ is closest to the template, and difference in height is closest. And it's also no-brainer that you check those ones. But the question is what you do about the other two. So how do you sort them? It's basically like if you need to compare tomatoes to apples. So how can we find something that, okay, so the solution actually that we proposed and that works quite well is basically to normalize it. And and I compute those TIs, and then we compare by an increasing order of TIs. But why did I choose IQ and height? Because IQ and height are actually independent of each other. Okay, they are not correlated. So you have big stupid people, small intelligent people, all sorts. Okay, so you can do a sanity check, and you can see that in case people have exactly the same IQ, basically this parameter boils down to what I was doing before. And are we done? No, because if they are not independent, what do I do? Well, luckily what happens, I'm not going to take more time, it would be a pity to throw away different measurements, because if I can, for instance, have age and height, we know that they are correlated because babies, they are not very high. Okay, so there is a correlation, so I can measure this correlation, but how I don't want to throw age by saying it's correlated. So there again, it's very easy to see. So you can correct it by simply computing the rows between the IQ and the height, which we assume to be 0, and then you have the row between the height and the weight, which is not 0, and then you can correct this, compute your TIs, and then generalize it with more correlations if you want. So when we applied this, it was actually turned out to be very good, because the average on the huge databases, they had like 20,000 people in the database. It allowed nearly to multiply by 15 the time that the identification was done, and without measuring anything new, meaning that what I call here height and IQ was derived from the template itself, but by a very, very small, very short processing. Okay, so thank you, and sorry for being late.
Questions, or do people want to go for lunch? It's a vote for lunch. No, Christoph.
I'm a bit surprised that you only managed 15 times, because, well, you have so high space. I would have expected that you need far less calls in the Oracle.
Why was it only 15 times? You would expect it a bit more.
This is what we found. It was because we're using the density of minutia, and the density of minutia was probably not very discriminating. But maybe with other criteria, size of the fingerprint or whatever, you can do better. But
right, okay, so lunch is in Wolfson Court, which is the college that way.